Lab on a chip uses unusual reactions between antigens and antibodies to diagnose diseases. We detect biomarkers to predict diseases, such as troponin I for myocardial infarction. On the chip for myocardial infarction, we use another antibody protein that binds to this protein. Antibodies that bind to troponin I are attached to a very small magnetic bead, and it binds to a very specific area on the chip. 2 million magnetic beads, with antibodies, are ready to be bombarded with proteins. Now, if you drop a small amount of blood on the chip, the microfluidic flow will allow the blood to reach the area where the beads are. If there is troponin I in the blood, the troponin I will bind to antibodies on the magnetic beads. Now, the combination will pass through the long pathway of the chip. This chip is lined with electromagnets that can pull the magnetic beads. The electromagnets are turned on and off, repeatedly. The beads will then oscillate through this pathway. Why do we use this technique? The answer lies in the pathway of the chips. At the bottom of the chip, there are about 2 million microscopic grooves, equal to the number of magnetic beads. And inside these microscopic grooves are other antibodies that can detect the troponin I. As the magnetic beads are drawn into the groove, the magnetic beads, not binded to troponin I, should slip out and make their way to the end of the pathway. But the magnetic beads with the troponin I fuse firmly to the antibodies in the grooves, so they can't escape. Only the magnetic beads with the troponin I form selective traps that remain in the grooves. Trapping the proteins like this is the key to this lab on a chip. If the magnetism is too strong, or switch adjustment is too fast or slow, the operation will not work. And it's important to remember that everything so far is happening on a microscopic and nanometer level that's invisible to the eye. We can determine the concentration of the troponin I in the blood based on the number of beads in the groove. Modern life has reached the point where it can detect a molecule on the nanometer scale with lab on a chip. Of course, not every company can reach this level of technology. So far we've talked about troponin I. But as we've talked before, our bodies are controlled by a myriad of proteins. Theoretically, we can understand that as long as we have the biomarkers, we can diagnose specific diseases. We can make a lab on a chip that detects microscopic amounts of viruses. If you can find the structure of the protein that's unique to the virus and the antigen-antibody pair, you'll be able to find traces of the virus that only exists in very small amounts of blood. You can attach different types of proteins to the chips to detect multiple diseases. That's why lab on a chips are a game changer in disease diagnosis and prevention. One of the biggest health innovations has come from thinking and looking into this very small world. Robert Wogan developed the microscope, and Leeuwenhoek was one of the first people to look at cells through a microscope. Thanks to them, bacteria were no longer invisible enemies, and we could save countless lives. Modern biotechnology has now reached the point where even the smallest molecules in our blood can be detected. All of these innovations are driven by the evolution of biotechnology, nanotechnology, and information technology, complementing each other. The digital healthcare industry has now become a strategy for major countries, including our country. But what's the point of advancing if it doesn't benefit everyone? No matter how cool it is? Even if we can detect diseases ahead of time, if tests are expensive, and they are not easily accessible, then we're missing something important. To achieve universal healthcare, we're going to have to prepare a lot of things to get us on the road to provide better accessibility, but most importantly, it needs our urgent attention.